Welcome, this is Coach Dorf. Today we're going to talk about section 2.6, which deals with limits at infinity and horizontal asymptotes. So I'm going to pull up my iPad here, share with you, and we're going to first look at the function f of x equals 1 over x. For that function, we know that the graph looks like this red part here, and that's a function we've talked about before. And I want to look at the limit as x goes to infinity of 1 over x. What that means is as x gets really, really large, as x is going farther and farther to the right, what happens to the graph of the function, the red part? Well, if I look at this, that means I'm looking at the right-hand side here. As x is getting farther and farther to the right, the red line is getting closer and closer to the black line. That black line is the horizontal axis, and that's where y equals 0. So the limit equals 0 because the red line is getting closer and closer to the black line, which is, again, the line y equals 0. Likewise, I could also look at the limit as x goes to negative infinity of this. And in that case, when you use this green part here, that means then that x is getting farther and farther to the left here. And what happens to the red line as I get closer and closer there? It's also getting closer to 0. So we can talk about limits as x goes to infinity or limits as x goes to negative infinity. Now in this particular case, they both equal 0 and they equal the same thing. That's not always going to be the case, as we'll see a little bit later. But this idea here leads to our first result. So we'll call this result number 1. And that is that a limit as x goes to infinity of 1 over x to the r equals 0 if r is greater than 0. And likewise, I have the limit as x goes to negative infinity of 1 over x to the r equals 0, again, if r is greater than 0. So quick example of that would be the following. Let's look at the limit as x goes to infinity of x squared plus 1 over x squared minus 1. Now, you could say, well, that function I have there that I just wrote down, this one that I'm going to circle in pink, that doesn't look like what I have in result 1. And you're right. This isn't exactly what we have in result number 1, but we're going to manipulate this so that we can get it to look like something in result number 1. And to do that, what I'm going to do is I'm going to take my original function there, I'm limiting it, and I'm going to multiply the top by 1 over x squared, and I'm going to multiply the denominator by 1 over x squared. So now, you probably have a few questions here, so let's talk about this. Notice that what I multiplied the top by and what I multiplied by the bottom by, or the numerator and denominator, it's the same thing. That means I'm multiplying the whole original function by 1, which is perfectly valid to do. As long as I multiply the top and the bottom by the same thing, it doesn't change the value or the result. Second of all, where did I get that x squared from? Where did I decide that I wanted an x squared here and an x squared here? Well, I wanted to have the same thing, the same number, so multiplying by 1, so they both have to be x to the same power. In this case, I picked x squared. Where does that x squared come from? It comes from the fact that I have a 2x squared in the original part there. And likewise, I have an x squared here. That's how I chose it. Going back to the problem then, now how do I multiply that 1 over x squared by both things here? I need to distribute it to both things inside the left parentheses. When I do that, that means I have the limit as x goes to infinity of x squared times 1 over x squared plus 1 times 1 over x squared. That's all in the numerator. And in the denominator, I do the same thing. I distribute that to both terms. When we say distribute, that means you're just multiplying it, but you have to multiply it by both of the terms in there. And so in the denominator, it's exactly the same as the numerator, except we have a minus between the terms instead of a plus that we have in the numerator. And then when I simplify that, this x squared times 1 over x squared is just 1. And on the right side, oops, let me use a different color here, that 1 times 1 over x squared is just 1 over x squared. Likewise, in the denominator, I'll have 1 minus 1 over x squared. Now, I can use that result I had earlier. I can use this result that I'm circling in blue, the limit as x goes to infinity of 1 over x to the r equals 0. In this case, r is going to be 2. Whoops, go back to my screen here. It's going to be 2. So my r is 2. And what happens in that case? That's going to go to 0 because of that result number 1. Likewise, in the denominator, that's going to go to 0. So when I do that, I'm going to end up with a 1 plus 0 on the top and a 1 minus 0 on the top, and I end up with 1 as the answer. So that tells me that the limit as x goes to infinity of x squared plus 1 over x squared minus 1 equals 1. All right. What if I had something that looked like the following? Let's look at example number 2 here. And in this example, what if I had 6x squared minus 1 over 2x squared plus 1? And I want to look at that limit. So I should have put that limit. Sorry. The limit of x squared minus, the limit as x goes to infinity of 6x squared minus 1 over 2x squared plus 1. Let me bring up Desmos here, see if I have that in here. Right. So gonna share my screen. Hopefully you can see this Desmos part here. And what happens to this graph is it looks like the following in green. It looks kind of like this and like this. And oops, that didn't work out right. This like this. So what's happening to the green part as we get further and further out? Well, it turns out that this is getting close to this line here, and this line here is y equals 3. And you may ask yourself now, go back to my iPad. So you may ask yourself then, how does this graph that we just saw on Desmos, how does it compare to the original function? Well, the graph is getting close to y equals 3, and look at my terms I have here. I have a 6x squared over 2x squared. What do I notice? Well, 6 divided by 2 gives me 3, right? 6 divided by 2 equals 3, and that matches up with this, y equals 3. So that gives me then result number 2. Before I do result number 2, we have to talk about something here. So call this a remark here. If I have a polynomial, so the degree of a polynomial is the value of the exponent on the largest term, on the largest exponent term. So for example, if I had something like f of x equals 3x to the 4th minus 5x cubed plus x minus 6, then the degree of f equals 4. And that's because this 4 matches the 4 there. That's the largest one, the largest exponent on that function there. So that allows me to get to result number 2. Result number 2. Suppose I have something like I have a polynomial over a polynomial, so we have a fraction. So let's say the degree of a equals the degree of g. Then the limit as x goes to infinity of 8 over g is going to equal the coefficient or the number of the degree term of over the coefficient of the degree term of g. So give you an example again. A different example than what we've done earlier. Let's suppose I had the limit as x goes to infinity of 4x squared minus 5x plus 1 over 3x squared plus 2. So going back from what we just did, so the degree of the numerator term equals 2, and the degree, because of this 2 here, let me use a different color here. The degree of the denominator term equals 2 because of this 2 there. So these are equal to each other. So by result number 2, the limit of these equals 4 over 3. Because that is the coefficient. 4 is the coefficient in front of the x squared term in the numerator, and 3 is the coefficient in front of the x squared term in the denominator. Now, on the homework, you can't just do this. So what you have to do is actually you have to show your work here. So how would you show your work? So you've got the limit as x goes to infinity of 4x squared minus 5x plus 1 over 3x squared plus 2. Well, we're going to do it just like we did earlier, and that's we're going to multiply the numerator and the denominator by the term 1 over x squared. All right. I'm multiplying by the same thing on the top and the bottom, so it doesn't change the value of the function. And I have to distribute it or multiply it by every term on the top and the bottom. And when I do that, I get then the limit as x goes to infinity of 4 minus, or let me write out all the steps here. So I'm going to get a 4, sorry, let me go back a little bit. I'm going to need a little bit more space. So I'm going to do limit as x goes to infinity. On the top, I'm going to have 4x squared times 1 over x squared minus 5x times 1 over x squared plus 1 times 1 over x squared. That's what I have in the numerator. Likewise, in the denominator, I need to multiply the 1 over x squared on the right by everything. And when I do that, I get a 3x squared times 1 over x squared plus 2 times 1 over x squared. And when I simplify that, I'm going to get a 4 minus 5 over x plus 1 over x squared in the numerator. And in the denominator, I'm going to get a 3 plus 2 over x squared. And now again, we can use the result that we had, result number 1 here. Let's see, my pen's not working. Let's see if I can get it to work again. Here, there we go. So by result number 1, this green part is going to go to 0. This is going to go to 0, and this is going to go to 0 in the denominator. And so I'm going to end up with 4 minus 0 plus 0 in the numerator, and 3 plus 0 in the denominator, which is going to give me 4/3, which matches what we had up here in this orange part. Same result. That shows us how we have to do it. Let me continue with result number 2. There's just a couple more parts I want to put in here. So also we have the following, that if the degree of A is less than the degree of G. Now remember, we were looking at this limit of H over G. So if the degree of the top part, the numerator, is less than the degree of the bottom, then that's going to equal 0. And an example of that was like f of x equals 1 over x, and the limit as x goes to infinity of 1 over x equals 0. Again, that looks like the function like this. And when we're looking at the limit, we're going farther and farther to that side. So that was like, we'll call this part B. Part C, if the degree of h is greater than the degree of g, then if I look at that limit of h over g, it's going to equal infinity. And an example of that is f of x equals x squared, and the limit as x goes to infinity of x squared is going to equal infinity. And if I look at the graph of that, right, that looks like this u, and as we go further to the right here, that's getting larger and larger, and that's why we get infinity there. Let me now say one more thing, and then I'll do another example here. So this section is on limits at infinity, which we've been talking about, but it also talks about horizontal asymptote. So let's say what a horizontal asymptote is. You know what a vertical asymptote is. That's where the denominator equals 0 if I have a fraction or a rational expression. And that gives me a vertical line going up and down so that the function gets close to it but doesn't cross it. In this case, for a horizontal asymptote, we'll say the line equals L is a horizontal asymptote of the function g equals f of x if either the limit as x goes to infinity of f of x equals L, or the limit as x goes to negative infinity of f of x equals L. So that's a horizontal asymptote. And as an example of this, again, remember that we looked at the example, the limit of 4x minus 5x plus 1 over 3x squared plus 2, as x is going to infinity, that limit, that equals 4/3. So the line y equals 4/3 is a horizontal asymptote of the function 4x squared minus 5x plus 1 over 3x squared plus 2. And again, let me go to Desmos here, and I'm going to bring up, hopefully I can bring this up here, that one. All right, here you can see this function, hopefully. So here's my red line. This is the graph of the function that we just did, and what happens to the red line here is I'm going farther and farther right. It's getting above 1, and it's getting closer and closer to that one line there, and that line is the line 4/3. So I'm just going to sketch that. Hopefully as this comes up here, my graph will look something like, oops, not like that, but getting close to there. And it's getting close to this line here, which was y equals 4/3. So that's a horizontal asymptote there. So this then gives us some creative type problems that we could solve. I think some of these can be fun. So let's see, find a formula. Here's one of these fun problems for a function that has a vertical asymptote, has vertical asymptotes at x equals -1 and x equals 2, and horizontal asymptotes at y equals 3/4. So again, if I have a vertical asymptote, that means that those happen when I get 0 in the denominator. So if I have x equals -1, that's equivalent to saying x minus a -1 equals 0, or x plus 1 equals 0. So I want to have that x plus 1 term, I want that in the denominator. Wait a second here. Sorry, I've got to make sure I'm sharing the screen there. Right. So that should be in the denominator. That green doesn't look very good, so I'm going to use a different one here, different color. And x equals 2, so that means I'm going to have x minus 2 equals 0, and that's going to be also in the denominator. So I'm going to have a function that has in its denominator x minus 2 and x plus 1. So here's going to be my function f. Now, I'm also going to have something in the numerator. And I need to figure out what is the degree, since it's going to have a horizontal asymptote at 3/4, that means the degree in the numerator and the degree in the denominator have to be the same. So let's go ahead and multiply this x squared, and multiply this together to get something without the parentheses. So when I do that, I'm going to get an x squared. So x times x times 1, negative 2 times x, and then minus 2. So I get in the denominator an x squared minus x minus 2. Since there's a horizontal asymptote at y equals 3/4, that tells me that the degree on top equals degree on the bottom. Because if it wasn't the same, if they didn't have the same degree, then either there would be a horizontal asymptote at 0, or the limit would go off to infinity. The only way it can go off to a non-zero number, or not to infinity, is if the degrees are the same. So I have to have a degree 2 on the top. So that implies I have a degree equals 2 on the top. And the ratio of the coefficients in front of x squared on the top and the bottom equals 3/4. So I'm going to, again, my f of x looks like this so far. So I have to have an x squared on the top, because that gives me the degree in the top and the bottom the same. And now the coefficients in front of them have to equal a 3/4, so I'm going to just put a 3 in front of here, and I'm going to put a 4 in front of here. Now I'm going to multiply everything by 4 in the bottom, because if I don't do that, it's going to change where my vertical asymptotes are. So when I do that, I get 3x squared, and on the bottom I get 4x squared minus 4x minus 8. And you can again go on to Desmos, and if you go on to Desmos and look at that, you will see that it will have the results that we want. In essence, basically on Desmos it should look something along this line. You're going to have this vertical asymptote at x equals -1. You're going to have a vertical asymptote at 2, so there's x equals 2. And you're going to have a horizontal asymptote at 3/4. So it's going to look like this. So this is the line y equals 3/4. And now when I graph the function in there, it's going to look something like this. Here it's going to go like that, and here it's going to go like that. That's what that function looks like. That's f of x equals 3x squared over 4x squared minus 4x minus 8. Let's do another example. Let's see which example I want to do here. Do this one here. This is going to be a harder one, or I shouldn't say harder one, but it's going to be a different one than we've been able to do so far. All right, so before we had a polynomial on the top and a polynomial on the bottom. Here we don't have a polynomial on the top because we have a square root. What's the degree on the top? Well, it's hard to tell you what the degree is, but I could tell you what the degree acts like. So on the bottom, the degree is 1, right? Because there's a 1 here, so that's degree equals 1. In the top, you might say, well, I have degree 2, but that 2 is under a square root. So it's really like a 2 times 1/2, which is like a 1. So the degree of the square root of 4x squared is a 2x, and that looks like degree 1. So how should I write that? Degree 1. So in essence, this acts like it has the same degree on the top and the bottom. So using that result 2, that limit of this should, I would guess, we're going to guess this here, it's going to be the square root of 2 over 3. I'm sorry, doing too many steps at once there. It's going to be like the square root of 4 over 3, which is 2/3. But let's prove this or demonstrate that this is true. So what I'm going to do is look at, showing this, look at the limit as x goes to infinity of the square root over 3x minus 5. So to do that, what I'm going to multiply by the top and the bottom by 1 over x. Where do I get the 1 over x from? The degree on the bottom is 1, so I want to do 1 over x to the first. And the degree on the top acts like it's 1 because I have the square root of x squared. And I want to make sure that they're both the same, and I want to multiply this all the way through. So I get the limit as x goes to infinity. When I multiply through here, this 1 over x squared goes to the x, and it goes to there. Now, I want to bring this in to the parentheses under the square root. I can't just bring in the 1 over x into the square root. I want to write it as something under a square root. So we're going to notice 1 over x is the same thing as the square root of 1 over x squared. So to write out all the details, what I'm really going to do here is multiply the top by 1 over x squared under a square root, and the bottom I'm going to multiply by 1 over x. Now, since x is a positive number, the square root of 1 over x squared is the same thing as 1 over x. They're just written in different forms. Now I can go ahead and distribute those. So on the top, I'm going to get the limit as x goes to infinity, and I'm going to get x times 1 over x squared plus 4x squared over 1 over x squared. And that's all under the square root. And in the denominator, I have 3x times 1 over x minus 5 times 1 over x. So then, when I simplify that, I get the limit as x goes to infinity. I'm going to get 1 over x to the first plus 4, and that's under the square root. And in the denominator, I'm going to get 3 minus 5 over x. And using that result, number 1 here, this 1 over x goes to 0, 5 over x goes to 0, and so I have the limit, well, I don't need the limit anymore because I've just evaluated it. So when you do this here, this is going to equal 0 plus 4 under the square root over 3 minus 0, which equals square root of 4 over 3, which is 2/3, which is what we had up here when we guessed it. So we guessed it and then we checked it to get it to work. Let's see, let me do one more example here. And which one do I want to do? Let's do the following example. It's a little bit different. Let's do the limit as t goes to infinity of, 2e to the t plus 1 over 3 minus e to the t. Okay, so the fact that I have t instead of x's doesn't matter. It's just a variable. What does the graph of e to the t look like? Okay, it's just like e to the x. It looks like this, equals e to the t. And so t is going off to infinity, so 2e to the t is getting really, really large. And in the denominator, you've got minus 4e to the t, and that's getting really, really large. So you have a large number over a large number, and that's 0 over 0. It's an indeterminate form. Doesn't tell me exactly what's happening. So what I'm going to do is I'm going to multiply the top and the bottom by 1 over e to the t. And 1 over e to the t, it's the same thing as e to the negative t. So you could think of it this way. And that means what's happening here, that limit, that's where we're looking at this left part here. And that's getting close to 0. So the limit of e to the negative t as t goes right here is going to be 0. Okay, so using that idea, I'm going to get the limit as t goes to infinity of 2e to the t plus 1 over 3 minus e to the t. I'm going to multiply by e to the negative t over e to the negative t. And I'm going to get the limit as t goes to infinity of 2e to the t times e to the negative t plus 1 times e to the negative t over the denominator 3 times e to the negative t minus 4 e to the t times e to the negative t. And then I get the limit as t goes to infinity of, what is e to the t times e to the negative t? That's the same thing as 1. So I get 2 plus e to the negative t over 3 e to the negative t. And again, what is e to the t times e to the negative t? So e to the t times e to the negative t. When you're multiplying things at the same base, you add the exponents together. So that's t minus t equals e to the 0, which is 1. So here I'm going to get minus 4 because this purple part, this is equal to 1, and this is equal to 1. So then, what do I have? Now I know, sorry, from what I mentioned earlier, this goes to 0, this is going to go to 0, and so you end up with 2 over negative 4, or negative 1/2. All right, I think that's enough for today. Hope that helps. Have a good day.